Okay, so today we're going to look at section 9.4, series. So what is a series? Series is the sum of the terms of a sequence. So if we take a sequence and we add up all the terms of the sequence, that's called a series. You can have an infinite sum or a finite sum. A finite sum is also sometimes called a partial sum when we add up a set number of terms. Okay. We need to talk about summation notation. So here is a sequence from a sub 1 through a sub n to infinity. So it just keeps on going, this pattern. Okay? So this symbol right here, this big fancy looking E thing, which is the Greek letter for sigma, when you see this symbol, it means that you're going to add up terms. This is what each term looks like. And this is a counter, or the index of summation, basically is what it is. And that means that you're going to go, k is going to go from 1 to infinity. So if I plug in the 1, I'll get a sub 1. Then I plug in 2, then 3, then 4, then 5, and keep going all the way up for infinity. And that's what that means. In a finite sum, same thing, you start with 1, then 2, then 3, then 4, and then you go all the way up to n and stop. So that would be what a finite sum looks like. If you have an infinity symbol on top, it's an infinite sum. If you have a number on top, then it is a finite sum. Here's a sequence. This is going to be a finite arithmetic sequence. It has a common difference of d. Then the summation right here is the same as this. So again, like I said, plug in 1 for k plus, then plug in 2 and so forth. So the summation needs to add up all the terms, of the sequence. And so how do I add up all these things? Well, believe it or not, a mathematician named Gauss, and I got the credit for this. And pretty much what you discover is this, that if I take the first term and add it to the last term, okay, and then times it by the number of terms there are, and cut that in half, that will be the sum. So he discovered that for us, and that gives you a formula that you can use to find the sum of a finite arithmetic sequence. Also, depending on the information you have, what if you don't have the last term? You just know how many there are. You can try and find the last term if you want, depending on how many there are. But I can also change a sub n, because there is an explicit rule for a finite sequence, arithmetic sequence, and I can use that, and I can plug it in for a sub n, combining like terms, and I get this alternate form of the formula, where I only need to know the common difference and the first term, and then how many terms there are. Most of the time, we just use this one right here. So we're going to write a summation notation and find the sum of that finite sequence. To write the summation notation, you need to find the explicit rule for this. You need to find the explicit rule. And we need to know how many terms there are. So I can see that there are 6 terms. So that means then in our formulas and such, n is going to be 6. This is an arithmetic sequence, so I need to know the common difference, which I can see clearly is I'm just going to add 4 each time. So that means d is 4. Okay, and the first term is -7. So I know by my formula for the explicit rule that I need to know the first term, which is -7, the common difference, and then n minus 1. So I get this rule right here. If I distribute and combine like terms, I'm going to get 4n minus 11. That is my a sub n. Once I have this explicit rule right here, I can now do the summation notation. Okay? So remember, the summation notation is this fancy E. Now, here it has N, so you're going to use a different letter. We're going to use K. And we're going to start at 1. This is the first term in the sequence. We're going to start with 1. We know that it goes all the way up to 6 terms. So this top number here will be a 6. So we're going to go from 1 to 6. You take this expression right here, your explicit rule, okay? Because this would be a sub k, which then becomes k equals 1 to 6, and a sub k is this, but with a k in there. So that is the summation notation. We use the formula that they just gave us on the other side, which says I need to know how many numbers are in a sequence that I'm adding. What is the first term? Add that to the last term and divide it all by 2. So as I work this out, 6 times 6 divided by 2, you're going to get 18. So there's the summation notation, and there is the sum. Okay? And you can see right there, pause right here, and you can write down the little notes that I had. What is the sum of a finite geometric sequence? So remember, geometrics is where we have a common ratio. Okay? So geometric common ratio is R, which is not equal to 1. Here's my summation. Finite meaning that stops at some value that some number. We're going to add up all the terms of that sequence. And so this is the formula associated with it. It's the first term, 1 minus the common ratio to the n power, so whatever that number up there is. And then the bottom is just 1 minus r. So that is the formula for that. And so let's do a problem that works with that. Find a sum of this finite geometric sequence. So we have a couple of issues with this so far. So to use the formula, and I'll write the formula right here. Again, it was a sub 1 minus r to the n over 1 minus r. I'm going to need to know, so the first term is 3. We can see that right there. I need to know what r is, and I need to know what n is. So the common ratio is pretty simple to find. You simply divide 2 consecutive terms. So 12 divided by 6 would be 2. 6 divided by 3 is 2. So I'm pretty confident r is going to be 2. The more challenging part, though, is I need to know how many terms I'm adding up. And I don't know how many there are because there's this ... in the middle, meaning I don't know how long it goes. So I have to figure out what position this item is right here. So what was the generic format, the general formula for a sub n and then a geometric? In a geometric, it was a sub 1 r to the n minus 1. Okay? That is the generic formula for a geometric sequence. So we're going to take this information that we have, and we're going to try and find that n right there. And we're going to use that number to do it, because that's the one I need to know about. So I'm going to plug in the 3 for a sub 1, the 2 for the r, leaving the n there. So I get 3 times 2 to the n minus 1, and that has to be this number right here. So we're going to solve this for n. So the first thing I'm going to do is going to divide by 3 on both sides, and I get 2 to the n minus 1. And this divided by 3, you can use your calculator, will give me 4096. Now, remember, to get to the exponent up here, I'm going to have to use the log. So I'm going to take the log base 2 of both sides, and that will give me n minus 1 is the log base 2 of 4096. So then add the 1. So n is 1 plus the log base 2 of 4096. And now I can find this value for n. And in doing so, plugging this into your calculator, n is going to be 13. Which means there are 13 numbers that I am adding up. So once I have that, then I can come down here and I can find the sum. So what is the sum as k goes from 1 to 13 of 3 times 2 to the k minus 1? That is 3, excuse me. Plug in the 1, you'll get 3. Plug in the 2, you'll get 6. Keep it in the comma, should be plus 12 plus dot 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 plus 12, 288. And what does that equal? Using this formula right here, 3, 1 minus 2 to the 13, 1 minus 2. And you can use your calculator, type this all in, and you will get this answer right here. And that is the sum of that geometry. So the main thing about this is, in the formula, you need to have all the 3 pieces of information. So if you don't have any of those things, you have to find it. Okay? So let's look at this one. An infinite series we kind of talked about already, but here it is right here. We're going to do the summation from n equals 1 to infinity. The index here can change to whatever letter you want it to be. That'll change quite often. Also, this little number right here can start at 1 or it can start at 0. It just depends. Okay? It doesn't matter. You can always generate the sequence out, the series out by just plugging in the starting value of this index and keep on going. So here is the infinite. Keeps on going to infinity. A partial sum is the sum up to a certain number. Okay, so we don't go to infinity. We stop at different locations. So what is interesting is that if we make this sequence of partial sums, so in other words, what they're saying here is this: what's the sum when k is 1? And you get a number. And then you get, well, what is the sum when k is 2? And then you get a number. And you keep doing that. So for example, I'll use this one up here to illustrate what I'm talking about. So the partial sum, the first partial sum, and they usually use a capital S, which is the summation when k equals 1 to 1 of this sequence right here, okay, of this sequence here is 3. So 3 is the sum. What is the second partial sum? Well, now I'm going to go from k equals 1 to 2 of that sequence, which is going to be 3 plus 6. And so that's 9. So these are the partial sums. If I can do the third one, k equals 1 to 3. That means we're going to add it to first three terms, 3 plus 6 plus 12. And so we just add 12 to 9, and you get 21. These are the partial sums, and they can be made into a sequence. And we can keep on going. Okay, so it generates a new sequence. So that's what they're talking about right here. So we're going to generate a new sequence of partial sums. Sometimes they converge to a number. We've already talked about that also. So what I'm looking at is, well, what happens if this partial sum keeps on going? And that's this notation you see right here. What is the limit as n goes to infinity? So as that gets bigger and bigger and bigger, the sum keeps on going. We keep generating more and more numbers. And so the question is, does it get closer to a number? Does it converge to a number? We did this in the last unit, the last lesson. And if it does, if the partial sums converge to some number, then that number is the sum of the infinite series. If the limit doesn't exist, then the series diverges. So the one we really mostly focus on would be the sum of an infinite geometric series. Okay? So I have a geometric series that's infinite, goes to infinity. A cannot be 0. This series will converge if and only if R, the absolute value of whatever R is, the common ratio, if it is less than 1. So if this number is bigger than 1, okay, or outside, smaller than -1, okay, then it will not converge, it will diverge. So it gives you a really easy way to tell if it's going to converge or not. If it converges, that it satisfies all this, then here is the sum. All I need to know is the first term and the common ratio. It's the first term divided by 1 minus the common ratio. Very simple rule if you have it. That's why it's an important one. You want to make sure that you know it. It does occur quite often in math from this point forward. So here's an example right here we're going to do. Let me pull it up over here. Determine if this series converges. If it does, find the sum. So the first thing I want to notice on this one here is the two things I got to do is I got to find the first term. Find the first term. That means take the 0 and plug it in. If I plug in 0, I'm going to get negative 4/5 to the 0, which is 1. That is my first term. And I need to find R. What is my common ratio? Well, it's pretty clear what the common ratio is. It's the thing in the parentheses. So my common ratio is going to be a negative 4/5. And because the absolute value of this is less than 1, okay, because it says determine if the series converges, you got to tell me why it converges. Because the absolute value of R, which is the absolute value of negative 4/5, is less than 1, the series will converge. So if it converges, then what is the sum going to be? The formula is a sub 1 over 1 minus R, the first term, and R. So the first term is 1, and R is a negative 4/5. So this right here is plus, so 1 plus 4/5 is 9/5. And so flip the bottom and multiply, so you're going to get the answer of 5/9. And that is the sum. And that's how that works. So mostly what you're going to be asked to do is find the sums using formulas and rewriting things into summation notation. Okay, so those are the two things you'll be asked to do the most. And we'll continue this in class with questions.